In this video, we're going to do a bunch of practice problems relating to L'Hopital's rule. So we're going to do a bunch of limits here. We're going to start all these problems the exact same way, and that is that we are going to plug in whatever value we're approaching in for x and see what happens. So if we do this here, we get 2 squared minus 4, which is 0. 3 times 2 minus 6, which is 0. That is an indeterminate form, but it is one that we can use L'Hopital's rule on. So that's what we're going to do here. So L'Hopital's rule here says that we're going to rewrite this limit as the derivative of the top over the derivative of the bottom. And that's going to give us the limit as x approaches 2 of 2x on the top and 3 on the bottom. Now, when we plug in 2 in for x, note this is a brand new problem now, we get 4 over 3. That's a real number, that's our answer, and we're done. Note that in this first example, there's another way that we could have done this, right? We could have done this problem by writing this as x minus 2x plus 2 over 3 times x minus 2. Cancel out the x minus 2's, and we can write this as x plus 2 over 3, and we get the same result, 4/3. So there's other ways to go about these problems sometimes, but we're giving ourselves more tools to take care of more limits, and sometimes L'Hopital's rule is going to be the only tool that we can use. All right, our next example, we're going to start by taking 0, plugging it in for x, and we get cosine of 0 minus 1 over e to the 0. That's going to be cosine of 0 is 1, so that's 1 minus 1. That's going to be 0 on the top. E to the 0 is 1, so this is 0 over 1, and that is not indeterminate. That's just 0. So why is this problem here? This may seem like the easiest problem we're going to do in this video, and it will be, but this is a problem that will get many students and give a wrong answer. I've put this problem on an exam before, and this is a difficult problem on the exam. Because if you are not checking for the 0 over 0 or infinity over infinity requirement for L'Hopital's rule, if you're not checking to see that it actually is indeterminate, you will be doing L'Hopital's rule incorrectly, and you'll be getting the wrong answer. This is a very simple limit. You just plug in the value, and you're good to go. Watch for that, and watch for that intermediately in a problem as well. Don't just assume that L'Hopital's rule is going to be what we need to do. We need to check each time. So L'Hopital's rule should not be used here. It cannot be used here as well. Next problem, the limit as x approaches infinity, natural log of x squared over x squared. If you plug in infinity into the top, natural log goes to infinity, so the square of that is going to go to infinity, and x squared also goes to infinity. This is an indeterminate form, but now we know we can use L'Hopital's rule on this. So that means that we're going to rewrite this limit as the derivative of the top over the derivative of the bottom. And note that to do the derivative of the top, we need to use the chain rule. So we're going to write this as the limit as x approaches infinity. The bottom is just going to be 2x. We can write that right away maybe. And the top is going to be the derivative of the outside, which is 2 times the inside, 2 times natural log, times the derivative of natural log. So we're going to do this step by step. We'll write this as 2 natural log of x times 1 over x. That's the derivative of natural log over 2x. And I'm going to go one step further, and I'm going to simplify this expression, because if I plug in infinity, I'm actually going to get some issues here. I'm going to get infinity over infinity on the top, infinity on the bottom. It's going to look weirder. So let's just try to simplify things before we go any further. We can write this as 2 natural log of x over 2x squared. And we can even cancel out the 2's while we're at it. So now when we plug in infinity, well, we still get infinity over infinity, but it's a little cleaner than what we did before. So we're just kind of cleaning things up with that algebra. And note that we're going to use L'Hopital's rule again. What I did in that algebra one more time is I just brought the x into the denominator. So L'Hopital's rule here says that we're going to write this as the limit x approaches infinity of the derivative of natural log, the top, over the derivative of the bottom, x squared. And that's going to give us 1 over x over 2x. And again, we can write that as 1 over 2x squared. That's going to be 1 over infinity. That is not indeterminate. We know that is going to be 0. So I want to say that I would say by the end of Calc 1, maybe even going into Calc 2, maybe even at the end of Calc 2, it might take a while, but at some point you should be able to look at that limit and you should just be able to know that that's going to be 0. And that has to do with dominance of functions. Polynomial functions dominate natural log functions. So therefore, we're going to have that the x squared is going to be bigger. It's going to dominate, so it's going to go to 0. If that doesn't make sense at this moment, that's fine. It will come later as you have more practice with limits. In the meantime, let's continue to do example problems using L'Hopital's rule. So next problem, we are going to plug in 0 in for x. That's going to give us 1 minus cosine of 0 over 0 plus 0 squared. That's going to be 0 over 0, 1 minus 1 on the top, 0 on the bottom. That's an indeterminate form. It's of the right indeterminate form, so we can use L'Hopital's rule. So this is going to be equal to the derivative of the top over the derivative of the bottom. And I'm going to stop writing ddx of the top and the bottom at this moment because we know that we're doing that with L'Hopital's rule. So the derivative of 1 minus cosine of x is going to be positive sine of x. The derivative of 1 is 0. The derivative of cosine is negative sine, and the negatives cancel out. And the denominator will be 1 plus 2x. If it is more comfortable for you to write the Ddx notation and to do that, please do that every time. I'm just skipping a step here because we know that's what we have to do. This is a brand new problem, so I'm going to plug in 0 for x and see what happens. I get sine of 0 over 1 plus 2 times 0. That is 1, sorry, not 1, that's 0 over 1. And that's not indeterminate, that's just 0. If you have 0 parts of something, that's just 0, not indeterminate. And therefore, we're done, and that's our answer. Next application. Find the limit as x approaches infinity of x to the 19th plus x to the 5th minus 8 over x to the 17th plus x to the 11th minus 6x squared. Well, let's try plugging in infinity in for x, and if we do this, we'll get infinity over infinity. So we can use L'Hopital's rule. And if we do that correctly, we take the derivative of the top, 19x to the 18th plus 5x to the 4th plus 0, 17x to the 16th plus 11x to the 10th minus 12x. When you plug in infinity here, you get infinity over infinity, and you can do L'Hopital's rule again. And what's going to happen the second time you do it is you're going to decrease the degrees of every single term, and we can continue doing that 17 times until we can see that we're going to be left with something on the top and 0 on the bottom. And this is kind of a way that we can see these rules for rational functions play out. After 17 applications of the L'Hopital's rule, this is just going to be equal to the limit as x approaches infinity of something times x squared over some number. And I don't know what number it is, so we'll just call it just some number and a different number here. The power is too bigger on the top than the bottom. That's what's going to happen, and you're going to be left with infinity in that case. So in this problem, I wanted to make clear that you can do L'Hopital's rule a whole bunch of times, and you can actually kind of guess how many times you're going to do L'Hopital's rule based on the degrees of these polynomials. Note that we would always do this problem just by saying that this is going to be infinity based on properties of rational functions. The degree is bigger on the top, so we know that it's going to go to infinity. But we can verify that with L'Hopital's rule. We know the degree on the top is bigger than the bottom. So we have no horizontal asymptote. All right. So we can do problems that we were able to do before. We can do them with L'Hopital's rule. Again, if you did L'Hopital's rule on this 17 times, I'd be a little bit concerned. There is a much easier way of doing it. We could do it that way. All right, next one. We have x e to the negative x. We're going to plug in infinity in for x. When we do that, we have infinity times e to the negative infinity, which is infinity times 0. That's an indeterminate form, but we cannot use L'Hopital's rule. So the strategy here is to rewrite this in a form that we could do L'Hopital's rule. And this one is kind of staring us in the face that we could write this as x over e to the negative x, or e to the positive x. And here, when you plug in infinity, you get infinity over infinity. And this we can use L'Hopital's rule on. So we're going to take the derivative of the top and the bottom separately. The derivative of the top is 1. The derivative of the bottom is just e to the x. So now, when you take infinity, plug it in for x, you get 1 over infinity, and that is just equal to 0. So again, we can't use L'Hopital's rule immediately. We have to manipulate this algebraically. We can't say anything about the limit when it was infinity times 0, but L'Hopital's rule allowed us to get it to a point that we could do something. All right, let's do some more algebraic manipulation. Here we have the limit as x approaches 0 from the positive direction. We need the positive direction because of the square root here. So let's plug in 0 in for x, and we get 1 over 0 minus 1 over square root of 0. And this is actually going to be like a positive number in both of these, which means that this is going to be infinity minus infinity. 1 over x and 1 over square root of x both have a very similar shape like this. So when you approach 0 from the positive direction, you're going to positive infinity. And here is our example of that indeterminate form that we cannot use L'Hopital's rule on yet, but we can do some algebraic manipulation to get there. And we're going to do this by finding a common denominator. So we can write this as the limit as x approaches 0 from the positive direction of, how about 1 over x? We multiply the first fraction by root x over root x, and we subtract the second fraction and multiply that by x over x. To combine this into one fraction, that's going to give us root x minus x over x square root of x. And now let's see what happens when I plug in 0. Here I get 0 minus 0 over 0 times 0. That's just 0 over 0. Indeterminate, but I can use L'Hopital's rule now. So this is going to be equal to the limit as x approaches 0 from the positive direction of the derivative of the top over the derivative of the bottom. Top is root x minus x. The bottom is x root x. So be equal to the limit as x approaches 0 from the positive direction. The top is going to be 1 over 2 root x minus 1. And the bottom, well, we can actually write x root x as x to the 3/2 power. You don't need to do product rule there. You can just write that as x to the 3/2 power, which will give you a 3/2 x to the 1/2 derivative. You can verify that with a product rule, but we can just do some algebra first to make that much easier. Now let's see what happens when I plug in 0 in for x. I get 1 over 0 here, minus 1, over 0. It's going to be infinity here. This goes off to infinity. This is like infinity over 0, which looks really weird, but that's just infinity. And that's not indeterminate. That may seem like it's indeterminate, but it's not. If you have a really big thing over a really small thing, that's a really big thing. How do we know this is infinity, this 1 over 0? That's for the same reason we said above. It's the shape of the function. As x approaches 0 from the positive direction, it goes off to positive infinity. We do need to kind of make sure that the sign is correct. If it were just the limit as x approaches 0 itself, then that limit might be a little bit different, might have a does not exist in it. All right, limit as n approaches infinity, root n over n. Let's see what happens when I do this. First of all, it's going to be nice to rewrite this limit as n to not the square root of n, but we can write that as to the 1 over n power. And this is going to allow us to think about how to plug this in. This is going to give us an infinity to the 1 over infinity, which is infinity to the 0 power. That's an indeterminate form. We cannot use L'Hopital's rule yet, but this is one of those exponentiation ones, so we can do the log trick. So the log trick says that we are going to rewrite this limit as e to the power of the limit as n approaches infinity of natural log of the inside, n to the 1 over n. E to the natural log, we can bring the limit out in front. So this limit now is what we're going to take care of. We're going to bring the e each step of the way. This is going to be e to the limit n approaches infinity, we can bring the 1 over n out in front. That's the log rule that we're going to do. And note that that's kind of the whole purpose of doing the log trick, is to use one of the log rules. If you're not doing that, then there's really no point to kind of bring in the natural log. We're making it seemingly more complicated so that we can use some nice rules to make it doable. So note that this is going to be equal to e to the, maybe we can write this as natural log of n over n. This limit, when you plug in infinity for n, you get infinity over infinity. This is actually one that we did before. We can do L'Hopital's rule. Note that each time I am bringing the e along for the ride, and I'm just rewriting the limit in the exponent. The derivative of natural log of n is 1 over n. The derivative of n is going to be 1. So this is going to be equal to e to the limit as n approaches infinity of 1 over n. That's like 1 over infinity. When you plug in infinity, that's going to be 0. This whole thing is e to the 0th power, which is 1. So note that if you didn't bring that e every step of the way, you would have just gotten 0 as your answer, and that's not correct. You do need to kind of bring it each step of the way, or remember that you have to do it at the very end. The log trick is to bring in a natural log, seemingly making it more difficult, so that you can do some nice algebra with logs. That is, you make exponents become multiplication, multiplication become addition, division could become subtraction. And you can actually do the log trick in many different circumstances. You can do the log trick dealing with derivatives or dealing with a whole bunch of different kind of things. The limit here is just one thing you can do with it. Log trick is an algebraic trick, not a calculus trick. All right, a few more examples. We have the limit as x approaches 0, cosine of x minus 1 over e to the x. I think this is actually one that we did before. I don't think I really meant to do this one again. This is just 1 minus 1 over e to the 0. Yeah, this is our 0 over 1, our 0. We did this earlier in the video. What I wanted to do was this one right here. Limit as x approaches infinity of 1 plus 1 over x to the x power. So when we plug in, I'm going to kind of bring this up here. When we plug in infinity in for x, I'm going to get 1 plus 1 over infinity to the infinity. That's 1 plus 0 to the infinity, or 1 to the infinity, which is an indeterminate form, but we cannot use L'Hopital's rule. But it's one of those exponentiation ones, so we can rewrite this using the log trick again. This is going to be equal to e to the power of this nasty limit. Natural log of, I should say, that nasty thing. 1 plus 1 over x to the x. And the whole point of doing that is to bring the exponent down out in front. So we can rewrite this whole thing as e to the power of, the limit as x approaches infinity, of x natural log of 1 plus 1 over x. And now let's deal with that limit. When you plug in infinity here, you get infinity times natural log of 1, which is going to be infinity times 0. That's an indeterminate form, so we need to kind of manipulate that algebraically. But we are able to do that, and we can write this as e to the power of the limit as x approaches infinity. We can rewrite this as natural log of 1 plus 1 over x all over 1 over x. And now when you plug in infinity, you get 0 over 0. And now we can use L'Hopital's rule. So let's do it. This is going to be e to the power of the derivative of the top. Let's even write this, derivative of the top over the derivative of the bottom. And this will give us e to the power of the limit. We need the chain rule on the top. That's going to be 1 over, that's the derivative of natural log. Leave the inside alone and multiply by the derivative of the inside. That's the derivative of the top, and the derivative of the bottom is negative 1 over x squared. We keep on going. Now we're going to finish that derivative. We have 1 over 1 plus, sorry, I forgot to write the limit, e to the power of the limit of 1 over 1 plus 1 over x. The derivative of 1 plus 1 over x is going to be negative 1 over x squared, all over negative 1 over x squared. And there's something nice that happens. Those negative 1 over x squareds cancel out, and we are left with e to the limit as x approaches infinity of 1 over 1 plus 1 over x. Let's plug in infinity. Let's see if this actually works. You get 1 over 1 plus 1 over infinity. That is 1 over 1 plus 0. That is 1. This whole thing is equal to e to the first power, or e. That is a very difficult problem. We dealt with a number of different indeterminate forms, 3 different indeterminate forms. You had to do the log trick. We had to do the dividing by the reciprocal trick. We had to deal some chain rules, some difficult derivatives, some algebra at the end. And then we had to do just finishing it all out, dealing with the limit. That's a very difficult problem, but it allows us to see actually another definition of E, that actually this limit is the definition of E. Sorry, this weird colon equals means kind of like defined by. You don't need to worry about that. All right, so that whole limit is equal to E, and that's in our definition of E. We had a similar limit that we looked at earlier in the year. That was the limit as x approaches 0 of 1 plus x to the 1 over x. You can kind of see the similarities between these two limits. That was also equal to E. That was another definition of E there. All right, one more problem, thinking about dominance of functions. So worded differently, but we're still going to do a limit. Check that any exponential function, that is e to the kx with k greater than 0, dominates any power function a times x to the p for a constant a and p greater than 0 as x goes to infinity. And for f of x to dominate g of x as x goes to infinity, we're saying that the limit as x goes to infinity of f over g is just equal to the limit as x approaches infinity of f. That f is so much bigger than g, or equivalently, f over g will be equal to, oh, sorry, not f over g, g over f, g of x over f of x is equal to the limit of 1 over f of x, and that would actually be equal to 0, where this would be equal to infinity. That's what it means to dominate functions. And we know that exponentials dominate polynomials. And we're going to verify that fact with L'Hopital's rule. So we're going to look at the limit as x approaches infinity of the power function a x to the p over an exponential function e to the kx. Note that when you do the limit here, when you plug in infinity, you're going to get infinity over infinity. That is indeterminate, but we can do L'Hopital's rule, and that's kind of the whole idea, is which going to be bigger, the top or the bottom? They're both really big. Which one's bigger? Which one goes to infinity faster? L'Hopital's rule says that you take the derivative of the top and the bottom separately, so let's do that. Here you'd have a times p x to the p minus 1, and the bottom here you would have k e to the kx. And again, you would get infinity over infinity, and you could do L'Hopital's rule. We'll do it one more time, and then we'll talk about what's going to happen. If you did it again, you'd get a times p minus 1 x to the p minus 2. P and a are constants, and at the bottom you would get k squared e to the kx. And what's going on is each time we do L'Hopital's rule, the top decreases in power by 1, and the bottom doesn't decrease at all. We still have e to the kx each and every time. So if we do L'Hopital's rule enough times, we have to do it p times the power, the degree of the power function. And this is eventually going to go to 0 over e to the kx. And that's going to be equal to 0 over infinity, which is 0. Or maybe just a number, the constant over e to the kx. The idea here is that every time you do L'Hopital's rule, the power functions decrease power by 1, and exponential functions don't change. So because of that, with limits at infinity, we could say exponential functions dominate polynomial functions. And there's actually a long list of, as x goes to infinity, some dominating functions. We know that exponentials dominate polynomials. So we can say that exponentials are, we're going to say, much bigger. That's going to be dominate polynomials. And polynomials are actually much bigger than, say, logarithms. Talked about that a little bit earlier. And actually, there's something bigger than exponentials, one that we're not going to talk about in this class, but you could say factorial functions are much bigger than exponential functions, which are much bigger than polynomial functions, which are much bigger than logarithm functions as x goes to infinity. And there's more we could do past that, but that's all we're going to need in a calculus sequence is those kind of things. So you'll talk about that more in a Calc 2 course. All right, that does it for L'Hopital's rule. A lot of different kind of problems we have to do. We need to check that we have 0 over 0 or infinity over infinity each time. If we don't and it's indeterminate, we can maybe manipulate it algebraically to get something using the log trick or common denominators or dividing by the reciprocal. And then it's just maybe a long problem to do the derivatives to get to the final answer.